Hello, my name is Roy Simpson, professor of mathematics at Kissimmee River College in Sacramento, California. In this video, we're going to go ahead and just do a bunch of examples of finding the Taylor or Maclaurin series expansions for given functions. And then we're also going to find the radius of convergence and possibly the intervals of convergence as well, because that's an important question. So the very first one here is just find the Taylor, or in this case, Maclaurin series expansion for f of x equals x to the fourth e raised to negative 3x squared. Well, we happen to know, and I'll write our theorems off to the side as we move. We happen to know already, we've proven this, and you can look back in the videos for this. We've proven that e is equal to its Maclaurin series expansion, n equals 0 to infinity of x to the n over n factorial. Thus, this e to the negative 3x squared, I can replace with the summation n equals 0 to infinity of, instead of x to the n, that's just for e to the x. Well, it's not e to the x anymore, it's e to the negative 3x squared, and again over n factorial. Generally speaking, we don't like to leave it like that. So what I'm going to do is first clean up the interior of the sum. And so this will be, let's see, a negative 1 to the nth, 3 to the nth, x to the 2n over n factorial. I know that looks worse, actually, but it is not. It actually allows us to see some patterns, like this is an alternating series, that type of thing. And finally, bring in the x to the fourth. So the summation n equals 0 to infinity, negative 1 to the nth, 3 to the n, and then we have x to the 2n plus 4, adding 2 to the power there, all over n factorial. Now, this is not a geometric series or anything like that, so to find the radius of convergence for this, we're going to use the ratio test. So by the ratio test, we require that the limit as n goes to infinity, the absolute value of a sub n plus 1 over a sub n, where a sub n is the sequence that the series is based on. This is a sub n right there. So we'll go ahead and say that's equal to the limit as n goes to infinity. Well, we'll go ahead and replace all the n's in that highlighted section with n plus 1s. That's 3 raised to the n plus 1. And then you have x to the 2 times n plus 1 plus 4 all over n plus 1 quantity factorial. We're going to multiply that by the reciprocal of a sub n, which is just the reciprocal of the given function. So that's multiplied by n factorial over negative 1 to the nth, 3 to the nth, and finally x to the 2 n plus 4. To save myself a little bit of time here, I'm going to make a little note that this right there is 2n plus 6, and also n plus 1 factorial is n plus 1 times n factorial. And that way we can see how this simplifies. Sorry, I had to close that absolute value. It's equal to the limit as n goes to infinity. Since we're doing absolute values, I don't really need those negative 1s, so I'm going to just get rid of those. This will be a 3 upstairs. Also, it'll be an x to the second power, because 2n plus 4's disappear. And downstairs is an n plus 1. And finally, the 3x squared can be pulled out front. It actually, you don't need absolute values on that because it's already positive. And you have the limit as n goes to infinity of the absolute value of 1 over n plus 1, which technically you don't need the absolute values on that either because it's already positive. But that limit will be 0 no matter what x is. So that's always 0, which is always less than 1. So our radius of convergence is infinite because, again, we can use any value of x. In other words, this function turns into this power series, and the radius of convergence of that power series is negative infinity, or I'm sorry, the radius of convergence is infinite, or in other words, the interval of convergence is negative infinity to positive infinity. All right, one other thing I should mention before we continue on with these is that I'm not going to force you to, in these examples, I'm not going to force us to prove that the remainder tends to 0. That is, we're going to go ahead and, if we can, assume f is equal to its power series expansion. And that, let me finish writing this. It's power series expansion. The reason why is because this gets very tedious to actually prove over and over again that the remainder tends to 0. So we did it in a previous video. I'm not going to do it here. Okay. All right. So that's a full example. Let's do an example B here. All right. So let's find the power series expansion, or the Taylor series expansion in this case, of f of x equals e to the negative x. But this time we're centering at -4. And so this ends up being, there's a couple ways you could do this. I'm going to be somewhat long-winded with it. We happen to know that, again, we're assuming that our function is going to equal its Taylor polynomial expansion. So this is going to equal a summation n equals 0 to infinity of the nth derivative evaluated at -4 divided by n factorial times x minus a -4 to the nth. Okay. And so let's go ahead and figure out what the nth derivative is in general. So as an aside here, I know that the function evaluated at -4 is just going to be e to the 4th. I happen to know that the first derivative evaluated at -4, well, the first derivative is actually a negative e to the negative x. So it's going to be a negative e to the 4. And the second derivative evaluated at a -4, well, that's actually going to be a positive e to the negative x. So this is going to be a positive e to the 4. And you can see that this pattern will repeat. It alternates back and forth between positive e to the 4 for even values of n and negative e to the 4th for odd values. So this polynomial expansion, n equals 0 to infinity, has an alternation in it. And I'm going to say it's n plus 1. Double check that, right? So if n is, oh no, it's going to be 0 actually. It's n plus nothing. It's just n. Sorry. Double check it. When n is 0, you get a positive number, which works, right? When n is 2, so you're taking the second derivative, it will also be positive. Okay, great. And then times e to the 4th all over n factorial x plus 4 raised to the nth. All right, so far that looks pretty good. So that's the Taylor polynomial expansion for e to the negative x. In fact, I should probably write that out. But that expansion happens to be centered at -4. Now let's see what the interval of convergence is for that, or what the radius of convergence is. And again, I'm probably going to use a ratio test for this. Ratio test. Because it's kind of the go-to. So limit as n goes to infinity. And since we already know kind of the punchline here, 1, I don't have to worry about negative, so I'm not going to worry about that. We'll have e to the 4th x plus 4 to the n plus 1 over n plus 1 factorial. I'm not going to write in all the little notes that I had before. I'm just going to immediately kind of hop into this. X plus 4 to the nth. Great. And things cancel. You can see the e to the 4th definitely cancel. This is going to be the absolute value of x plus 4 times the limit as n goes to infinity of 1 over n plus 1. I actually didn't need the absolute value, but whatever. And that will equal, if I can move my screen, for some reason it's not moving, there we go. That's equal to 0 always. So because it's equal to 0 always, the radius of convergence is infinite, and the interval of convergence is negative infinity to infinity. So the question is, why would you even bother centering it anywhere else? You wouldn't, probably. However, well, that's not true. You could center it at -4 if you were trying to approximate e to the negative 3.2, and you only wanted to maybe use the first 5 values of this summation. That is that is perfectly fine. You're centering somewhere near to -4, or I'm sorry, -3.2, which means you don't need to do a lot of your expansion to get a good approximation for e to the -3.2. Anyhow, not that big of a deal. Okay, so next one. Let's see what we have coming up next. See. F of x equals cosine of x. And we'll go ahead and do this about 0. So we just want the Maclaurin expansion. Now, here I'm going to be a little more rigorous. I'm going to go ahead and, since this is such an important one, I'm going to go ahead and not only find the Maclaurin series expansion, but I'm going to prove that f is actually equivalent to that. So in other words, that the remainder tends to 0. And you can, again, for the idea of the proofs, you can go to previous videos to see that. But here, again, I know that not cosine, but I know that the Maclaurin series expansion here, and I'm still going to call it T sub, no, I won't use T sub n. I'll just do this notation. Maclaurin series expansion is this, where you have the nth derivative evaluated at 0 over n factorial. And then you have x to the n, x minus 0 technically to the n. Okay? And so we're going to go ahead and take a look at the patterns for the derivatives. So again, as an aside, the function itself, actually maybe I should have two things going on. The function itself is cosine. So its first derivative is negative sine. Let me write that in there, negative sine. And its second derivative is negative cosine. And its third derivative is a positive sine. And finally, its fourth derivative gets right back to the cosine. So there's the pattern right there. You can see it now repeats forever and ever and ever. But not only that, we need to evaluate these at 0. So f at 0 is 1. F prime at 0 is 0. F double prime at 0 is a -1. F triple prime at 0 is 0. The fourth derivative at 0 is back to 1. So 1, 0, -1, 0, 1. That's going to be the pattern. So let's go ahead and take a look at this. Just expanding it out. This is going to be, let's see, 1 over, so the 0th derivative, which is f itself. So when n is equal to 0, we get the numerator is 1, the denominator is 0 factorial, which is defined to be 1, x to the 0th, plus the first derivative at 0, which is 0, plus the second derivative at 0, which is a -1, x squared over 2 factorial, plus the third derivative at 0, which is 0, plus the fourth derivative at 0, which is 1, x to the 4th over 4 factorial, plus 0, and you can probably imagine what the next one's going to be, since it has this alternation in it. It's going to be plus a -1 times x to the 6th over 6 factorial, and so on and so forth down the line. So how are you going to compress that down into a nice single summation? Well, this ends up being, let's see, a summation n equals 0 to infinity. We'll have an alternation, so I'm going to say a -1 to the, let's start with -1 to the nth. It's always good if you know you have an alternation to start there and then test. And then notice our powers on our x's here are all even. So that means we have x to an even power twice n is a good way to put it. And by the way, those denominators are those same powers but factorials. So I'm going to put 2n and then a factorial sign here. Notice I put a parenthesis around the entire 2n. It's not 2 times n factorial. It's 2n factorial. So anyway, let's test this out. When n is 0, let's just try this out. When n is 0, I get -1 to the 0th, which is +1, x to the 0th over 0 factorial, which is 1, which is exactly what that is. When n is 1, you get a minus x squared over 2 factorial, which is exactly what that is. When n is 2, we get -1 squared, which is a plus, x to the 4th over 4 factorial, which is the next one in line. So I'm pretty convinced that this is the pattern. Okay. Now that's pretty neat if that's actually equal to the function. To show that that's equal to the function, we're going to have to use Taylor's inequality, right? We need the remainder to tend to 0. And that's from a previous lecture where we said as long as the remainder, this guy right here, tends to 0 for the nth Taylor polynomial, then we know our function is actually equal to the Taylor polynomial expansion. And to find out a bound for the remainder, we're going to use Taylor's inequality, where the n plus first derivative is what we're trying to bound. So let's go ahead and go back to the problem. All right, so let's see. We want to showcase that the remainder is bounded by something over n plus 1 factorial, and then x to the n plus 1 power. By the way, the remainder is always greater than 0. So let's see, the remainder. I happen to know that m will be the bound, so I'll say where. M is the bound on the n plus first derivative at any value of x that I so choose. Well, I know that the n plus first derivative for our function, which is the cosine, it doesn't get any bigger than 1, right? So I know that no matter what derivative we're at, the derivatives, the function or the derivative that we're at is always less than or equal to 1 in magnitude. So this is what I'm going to choose to be my value for m here. So I happen to know that my remainder for the nth degree Taylor polynomial is equal to or is less than or equal to 1 over n plus 1 factorial x to the n plus 1. And we have actually shown previously, specifically right here, that, and you can go back to a couple lectures or two to find this proof, but we've shown previously that this limit is equal to 0. Hence, we know that the limit of this guy will tend to 0. The limit of this guy will tend to 0, obviously. Thus, the remainder tends to 0. By the way, I'm not being super rigorous here. I should be using limit notation, but we've already actually proven this in a previous problem. So I'm just going to say the limit as n goes to infinity of r sub n is equal to 0. So it's technically the absolute value. And so therefore that implies f of x, or maybe I should say cosine of x, since that's what f of x is. Cosine of x is actually equal to its expansion, n equals 0 to infinity, negative 1 to the nth, x to 2n over quantity 2n and quantity factorial. So I just want to be rigorous on at least one of these problems. So there you have it. This is a very famous little theorem. So I would say that it's easily memorizable. There's one for the sine as well. The sine, which I'm not going to prove here, looks like this. The sine of x is actually equivalent to the summation n equals 0 to infinity. Again, it'll have an alternating pattern, but sine is an odd function, so it's a sum of a bunch of odd powers all over 2n plus 1's factorials. So that's the power series expansion, or the Maclaurin series expansion for the sine right there. And a little side note, we do need to know the radius of convergence for this, so we might as well just compute the radius of convergence for the cosine there. So let me scroll down using the ratio test. This is actually something you could easily do on your own, but we'll just do it real quickly. Limit as n goes to infinity, absolute value of, I'm going to remove the negative, so x to 2n plus 2, technically, over 2n plus 2 factorial times 2n factorial over x to 2n. That was me substituting n plus 1 into the thing. And this will clean up to be the absolute value of x squared, which doesn't need an absolute value, times the limit as n goes to infinity of, I'm not going to use absolute values, I don't need it, but 1 over the quantity 2n plus 2 times 2n plus 1, and the 2n factorials cancel, and that will tend to 0 no matter what you do. So which is less than 1 for all x values, or values of x. So therefore, the radius of convergence is anything because any x value will work. That is, that power series expansion is true from negative infinity to positive infinity. We have convergence. All right. And as a final example, we'll just do one more here. Since we're finding Taylor or Maclaurin series expansions for given functions, let's go ahead and make a function that is a product of maybe a polynomial and a cosine with a nesting. And when I say nesting, I mean a composition. So let's see, if you're given a function and it's the product of a polynomial times another non-polynomial function, you leave the polynomial part on the outside for the time being, and you say, well, I happen to know that if I had the cosine, it would be -1 to the nth, normally times x to the 2n over 2n factorial, normally. That's if I was looking at cosine of x. But I'm not looking at cosine of x. I'm looking at cosine of 1/5 x squared. So I'm going to spend a little bit of time cleaning this up. Not too much, but just a little bit of time. I'll leave the 2x outside for now. N equals 0 to infinity. I have the alternation in here. I'm going to park that 5 downstairs. It'll be 5 to the 2n downstairs. And there's still a 2n factorial in that denominator as well. And then I have x squared to the 2n, or in other words, x to the 4n. Whoops, I almost miswrote that. And now finally, I can bring in the 2, or I'll probably leave the 2 on the outside because it's not going to make much of a difference. But I'll bring in the x because that would be bad form if I didn't. So this is n equals 0 to infinity, -1 to the nth, x to the 4n plus 1 over, you could actually write this as, if you wanted to, as 25 to the n. There's nothing wrong with that, times 2n factorial. Now remember, we do want the radius of convergence on this. However, I'll just leave it to you to showcase that the radius of convergence is infinity. Okay. And let's see, I think we're good. All right. Stay tuned for another lecture.